Okay. He's here. He's here. Oh, no. Okay, let's get. All right, great. Let's get started on the panel. And for the panel, I prepared a couple questions, a few questions for the panel, but I'd love to get people engaged. So feel free to put up your hand with questions or comments during the talks, and we'll just have it, ideally have it be free form so people can say what they'd like, both in the audience and up here, okay? Let me, now all these people have spoken recently, but I think just to start, maybe you could introduce yourself and say a little bit about your work in domain adaptation. I know Percy's kind of said that moved on from there, but let's, and Shai gave us a good history, but why don't you just, as a quick introduction, say a little bit about that. So we'll go down the road this way. So go ahead, Shai.
Okay, so yeah, I mean, as I just told you, I mean, I started on this area 20 years ago, and by coincidence, just because I met those people at the conference. And I worked on this topic, I think, pretty extensively for about maybe 10 years. And then I felt that I'm not making as much progress as I would hope, as I would feel happy about. And I moved on to other things. And then I see new people came in, and some of them rediscovered old results, which I couldn't allow myself to do. And there's also some progress, and I'm completely baffled by the success of LLMs, and I feel like, are we still relevant as theoreticians? That's a question for discussion. Okay.
Great.
I think I first started getting into domain adaptation with that actually same Blitzer work when I was I guess back in grad school, and I was really interested in this idea of how you can do I guess it was transfer, but the fun important part of transfer is the domain adaptation part. And maybe I don't know if I exactly worked on it, but it sort of came up all the time as through my NLP work, right? And develop benchmarks for domain. I guess you can call it domain adaptation or domain generalization, where getting people to think beyond IED, because it was clear if you just were in IED's situation, you would be sort of fooling yourself into thinking you do better than you actually were. And then foundation models came along, and then it seemed like, I remember, I guess through the sort of the clip era, it was this feeling that, well, all these methods that worked on domain adaptation kind of didn't really matter. You just needed these foundation models, and they could actually address a lot of the issues empirically, even though we might not understand how they work. So then we try to understand a bit more how they work. And then most of my work since then has been shifted on just understanding foundation models and leveraging them.
So, so my kind of background over here is, I guess my home community is learning theory. So I have been a learning theorist for a long time. I also work on AI privacy. So domain adaptation or distribution shift or whatever you might call it is something that comes up quite a lot, right? In learning theory, you try to do certain things and then you realize, wait a minute, this is exactly what happened. There was a shift, and so this is why it work, right? And so I have been on and off interested in the theory of distribution shift for a long time, and and occasionally I write a paper on it, and that's kind of how I'm here.
I've studied distribution shifts for most of my research career, but the field was very short in this crowd. So I echo Percy's sentiment that, especially in the clip era, Alec and Jung-Wook Kim, it was really inspiring, right? That data scaling could have that big an impact. But at the same time, as someone who has one foot in operations research, I think a lot about problems where the labels are generated by humans. And there is, I think, really a continual data scarcity that you have to grapple with. And you genuinely need agents that can understand what you don't know and try to gather more information on those types of data points. So these are topics I think about on a daily basis these days.
Okay, great. So then that leads well into the next question, which is, we've all seen that attention is all you need. So one claim is that scaling is all you need, right? So the question here is scaling all you need? And so does that make all the problems that we've been talking about this week go away? So why don't we start at that end this time? Hong, you could take that up. Yeah.
I think I do believe that scaling is all you need, except that only works in a post-scarcity world, right? Without resource constraints. So if you have resource constraints or you need to access proprietary data, or if you're in healthcare, right? You have all kinds of different constraints you got to operate under. And then you have to be much more mindful about how you scale. And I feel like we've kind of depleted web data as of a year or two ago, or maybe even before if you're at OpenAI or Anthropic. And at this point, I think you actually do need to be extremely thoughtful about which new data set we're going to go out there and collect next. And this, I think I'm a big proponent and a big believer of principled thinking. And my sense is that theory-trained people can perhaps develop approaches that can inform this endeavor.
Let me just ask a question about that. So that sounds to me like smart scaling is all you need. So it's like now you just have to go find the right data, and once you find the right data, you're done. So is that
Smart scaling is better than dumb scaling.
Yeah.
Maybe. You want to?
So I don't know. I was I was going to kind of add to some of that, but then the thing that has happened is that, look, when we have scaled these things up, a lot of the problems that we wanted to solve, there's a lot of data for, right? So those problems are being solved well. But now there are other problems that are not being solved as well. So distribution shift is there, but I feel like it has moved to, for example, parts of the tail. So to give a concrete example, right, a lot of the, like the ImageNet distribution shift kind of problems that we wanted to solve, like waterbirds and so on, the bigger models like Clip can solve them. But now Clip has its own issues. So for example, the web data has very little geographic diversity. So there are all kinds of benchmarks where you try to use these models which are trained on internet scale data, and they can't, identify stoves in Nepal because, they haven't seen examples of stoves in Nepal. So I think the problems are still there, but they have just moved to a different part of the space. And no matter how we scale, the problems will always be there. They will just move further down. So that would be my.
I think I sort of object to the framing of the question, which I don't really like this question, because in one sense, it's clearly not the case, because, we had all this internet data, pre-transformer. We had it, 20 years ago, and we certainly didn't have ChatGPT. And so if you're scaling, and we had compute, we had nearest neighbors, we had a lot of things, but that didn't get us to where we needed to be. And remember, there was an era where Google would say like nearest neighbors is all you need, and clearly it wasn't all you need. So I think clearly there's algorithmic innovations, transformer, which came from like attention and having all the deep learning things. Maybe you can call them hacks or little ideas, but somehow all of this came together, with Adam, and, which you can also think of as like, it works as an optimizer, and somehow all of this comes together, and you need all of that for things. So it's never, scaling doesn't even make sense by itself, because what are you scaling? So it's a sort of the combination of the architecture and also the data. And nowadays, people talk about we're running out of, good high quality tokens and internet, which means that you need to be more clever about how you collect data or, synthesize data. And that's going to create a lot more innovation. And furthermore, even mere scaling up, it's not like you go into your config file and you just add another 0 and you press enter, and that's how it works. There's a lot of systems and efficiency work that happens, and all of that is part of what is meant by scaling. So I feel like the whole scaling is what you need. It's a very kind of reductive way of thinking about all the different layers.
So I will of course object. So I think that we have a tendency to look at the half full part of the glass. I mean, there are so impressive achievements of foundational models and LLMs, and we focus on those impressive unexpected achievements, and we kind of don't see the failures, and there are failures all over. Like what happened on we had the prediction that this election is going to be completely even, completely tied. Boom, nothing. we couldn't predict it. Try to see what is happening with trying to predict storms or weather. Or I mean, sure, the half full of the glass is very impressive and very shiny, but we should not forget that there is a lot of areas in which we are not doing so well, and in spite of almost exhausting all the scale that we can, as you're saying. I mean, the same thing is with medical data. The same thing is like you were saying with small groups. Like I don't feel that machine learning with scale solves all the problems. I think it leads to another interesting question. I mean, what can we hope for? And even if we just try to compare it to the abilities of humans, I mean, how did we get all the abilities that we have? And where did it come from? And I think it's an interesting question, but I don't think that machines are about to be able to compete with us on every task.
So maybe if I can kind of summarize the take. So I think what we are getting at is what is possible with current technology, right? Like, deep learning is great. There's absolutely no question, but they're also like very, very data hungry, right? They're not as data efficient as humans, right? So maybe what we're trying to get at over here is we need to make things more data efficient.
Last question, like setting aside like the extremeness of the statement of scale all you need, there's I wanted to distinguish maybe two important types of tasks. There's tasks like recognition tasks where there's a single function that's useful at every single place at every single point in time that gives the right answer in every setting, and it's just a question of like growing the support. Like the function that looks at an image and says, is there a dog in it? And for this kind of task, it seems if nothing else, whether or not it's all you need, there's certainly like a tremendous profit in training a model on all the images from all the periods of time from every corner of the internet. And there's a different family of tasks where the actual prediction is sensitive to the context. Like you want to predict based on a set of patient and doctor characteristics, whether a patient's likely length of stay is. You want to predict their likelihood of getting sepsis. It's going to be different given the same set of covariates at a different hospital at a different set time. And the indiscriminate pooling of data like doesn't work in the same way. And to what extent does this like vis-a-vis considerations of like adaptation or generalization, are we often like slurrying those two types of tasks in our head and like failing to make like a really important distinction? And I guess I'm in particular interested in how folks think about the latter, which is where there's not like a universal model where if only we pull the data, we're good. But we actually do need to be somehow context.
I wanted to title my talk initially, before I realized I'm giving the last talk, about domain adaptation beyond dogs and cats. And I think that the point of the beyond, I think it connects to what you're saying. I mean, if we have tasks in which we want to succeed on the average or with expectation, then we're doing very well. But if we have tasks where we have an individual and we need to predict whether this individual will get sepsis or not, or then when the loss can have a spike, and we want to know, is this instance within the scope of what we understand we are very far from understanding it, and I don't see that just scaling will solve it.
I mean, I think that, I don't know, I used to look at more of the glasses empty part. I wrote all these papers on adversarial examples and look, haha, this model is vulnerable in this way. And after a while, it just kind of got old because, it's saying, well, these numbers, which look like 90s, I can bring down to maybe 60 or maybe 0. But it fundamentally doesn't, it's okay, now we know, we can kind of move on. And also, I think a lot of, Ludwig Schmidt's work, I think also shaped my, thinking where, you plot the in-domain accuracy versus out-of-domain accuracy. Most things kind of lie on this line. And one of the few things that moves you off the line is, larger, pre-trained models. So while I do think that it is important to evaluate on, out of domain, because that's what, if you care about the actual accuracy and know that, hey, wow, we're getting 50% accuracy, better not deploy this in a hospital, that's good. But from a machine learning research perspective, this doesn't really, I feel like this interventions that you would make of, let's bring a large model, language model into, because it has all this prior knowledge from outside this domain, actually is really, helpful. And I've seen a lot of cases, I mean, even in these small domains where you just have the richness of the knowledge and ability to, reason, and that's actually just extremely helpful for these very small domain settings.
I don't know if anyone answered the question.
I'll answer. Can I try to?
Question.
Okay.
Yeah, so going back to Zach's question. Interesting answers, but I don't know if they actually address the question. Yeah.
I do think we need methodologies that allow us to scale up in those domains that have genuine confounders, right? And it requires a great deal of human reasoning right now in order to come up with semi-reasonable models. And web-based priors, I guess you know better than anyone, it works wonderfully better than most robustness interventions. But at the same time, I feel like the accuracy on the line type of phenomena, it just breaks when there is genuine confounding. And I don't think that the current way of increasing the support is going to fix the problem. So when I said scaling is what we need, I think we need different ways of scaling and different ways of thinking about adding in additional data information. I'm not quite sure what that interface would look like though. Maybe incrementally adding more features or something like that.
Yeah, let's say, just to act as a panelist, I think it's still a question of smart scaling in that case, right? So as you're saying, you don't want just indiscriminate data. It's not going to be relevant probably to some particular medical condition, some particular hospital. You need all that information. But so to some degree, you'd like to get as much data as you can from there, but it is a question of both on the modeling side and the data side, collecting the data that you think is relevant. I think the interesting question is, what we're finding in our current models is that often what turns out to be relevant is some general reasoning, like how what Percy was saying, that things that do transfer. So I think it's an interesting question of, could you, if you can't collect the specific data that you'd like to, that are relevant to the particular condition you're trying to diagnose, are there other things that are related to it that will be valuable as, we don't have enough data in some other regime. So I think that's a whole open question for the field.
I guess like the accuracy on the line kind of like work, like Ludwig's work on like image recognition, is tackling precisely the setting where there is a common model that works in both settings. Like it's not a setting where domain, like adaptation of any kind is intrinsically necessary. What's really necessary, like the end run around it is just get closer to like the universally better model, and then you're just good in every setting out of the box. But like what it doesn't give is like a program for like what's left over when you've milked all that you can out of that. Still, what is a set of routines for the settings where adaptation is fundamentally necessary?
I would say that you should always be in a setting where there's no context, right? If you want to make your context rich enough that it's a clear issue, and then the game is just to get it out. So
just part of the input is where are you and
which hospital are you? I think it's just
at what point in time are you in?
Yeah, I think there's just like so much kind of metadata and information that traditionally has just been impossible to, you just like not use it. And if you use it somehow, then and you leverage, if you sort of connect it into the language space where you actually know something about, like, oh, this is an Oklahoma, and well, I have read this other study, and I don't know what's going on, but it's possible that you're leveraging additional information that you wouldn't have if you just treat it as a.
I think it relates to what you were saying is that sometimes it's a matter of having different features. I mean, the feature of which hospital you are, maybe you did not use it when you had your big data. And sometimes we have to go into different features, into different representation, not in terms of combination of the current features.
To what extent do you think that expansion requires human domain knowledge versus maybe there is a one-size-fits-all solution? Because I feel like the ImageNet framing kind of, I feel like Ludwig became a domain expert on YouTube eventually and knew all the different idiosyncrasies.
I was on a couple of those papers. For it's worth. It's not an ImageNet phenomenon. It happens on everything. Every place we looked, it happens.
So what happens to define
So you
accuracy on the line?
yeah, whatever.
No,
I hate that that's what it's
No,
called.
but-
Oh, yeah, okay,
Whatever.
that's what I mean,
fine.
yeah.
You train on a
Okay.
data set, you
Yeah.
get all these different models, you train on for however long you want. And then you build it, you try to build as close to an IID test set. Actually, it doesn't matter. You build some new test set, and then you tend to see a ordering where the ones that did well on your first thing do well, do better. But they all tend to do worse, except when they all tend to do better. And you don't know when it's going to be hard and when it's going to be easy.
So you think
I don't think the trend is,
The ordering seems to be very, invariant.
Yeah.
But
I don't think the trend is that strong on Iowa Scam or other tabular data sets where you genuinely have information
no,
that's
I
not
mean,
measured.
we have a paper where we looked at like 190 cackle competitions, and you just see the same trend everywhere. How many data points do you need? We need like 100.
Tell us about the
Okay,
Okay, tell us about the counterexample.
I mean,
Okay.
there are clear cases like Zach mentioned.
I want to
where-
say for the record that Samori made us come in here to stir the pot.
Well,
Like-
I wasn't, I'm not even stirring the pot. I'm just like, let's be. I mean, I saw the plots. I know what they look like.
I mean, to your point about human domain in intuition, I mean, that's exactly what a lot of that's internet text, right? That's all the production of humans' thoughts and experiences and facts kind of written down, but that's getting ingested and brought to bear on problems. So
I don't think that all of human knowledge is in the internet.
I hope not.
What happens if you're trying to take clinical notes? Do you think, and in a very robust way, do you need a lot of human knowledge, or does knowledge on the internet actually suffice?
well, okay, so I think there are a lot of knowledge. For example, there's textbooks, and then there's all of the clinical notes and EHR data inside hospitals, which is like clearly a treasure trove in terms of information. And it seems like you ought to be able to get an incredibly rich representation of what the hell is going on in the hospital and I mean, it's obviously like lots of serious correlations on all that, but it does seem like the information theoretically, there's stuff there that you should be able to extract if you're clever about it.
So it's a bit of a change of some questions, but I just want to ask a question that is it may be a bit not too nice, but the answer is pretty nice. But so are there directions of research around distribution shift that we believe are just the wrong direction, we should be terminated? And it's a tough question, but it's to ask it in a better way. Are there directions of research and distribution shift that we feel like we probably should put the most effort on at this point?
Can I let Ben answer this question?
Yeah, no, but I already gave you an answer to this negative thing. I think the attempt to have a general theory of domain adaptation, regardless of the concrete application, I think it's bound to fail. I mean, that's a direction. And
That's what I was gonna say.
What?
That's what I was gonna say.
And I will also agree with Shai, as I said in my talk, I will also agree with Shai, right? It's yeah, one should look at specific kinds of domain specific applications, things like that.
I mean, I guess maybe one thing I find is that a lot of domain adaptation is still kind of in this, XY kind of supervised learning regime. And if you think about what's going on with foundation models, is clearly not, I feel like that's a wrong level of abstraction, because it's just sequences of, tokens in documents being trained on for next word prediction. And then at test time, you can do various things, instruction following and context learning. And that looks nothing like, XY, pairs. So I feel like even when I, was thinking about in context learning, I think I was always saying like, we're not like in context learning with the XY pairs is, I don't think it's missing sort of the deeper phenomenon, which is some sort of transfer between almost sequence prediction problems. And maybe that's like, I feel like we need some new abstraction to think about that.
Actually, to add to this, there are a lot of, in these language models, when you're talking about things like question answering tasks, right? There are lots of examples of distribution shift. And actually an example, you gave in your talk, right? You were talking about this paper where this is an AI safety thing. If you ask the model, how do you build a bomb? It'll say, no, I cannot tell you. But if you ask the model, how did people build a bomb? They will tell you, right? Because that was a context shift, right? So these kinds of, there's a lot of these kinds of problems. And maybe that's something we need to look at a bit more.
Yeah, I think to follow on what Percy was saying, I mean, I didn't want to give the positive thing because I want to keep it to my students. But I completely agree with Percy that this paradigm of XY training is completely not reflecting what is really happening. And we should come up with a paradigm that can try to reflect the way we're training foundational models. And it's not, I mean, I cannot just measure the D of PQ between the data of the foundational model and the data that I want to apply it to now. They're completely different distributions, no connection between them whatsoever. And I think that trying to understand how those things work is a very challenging but kind of promising area, because we are very far from scratching the surface there.
Maybe just to add to that, because we now have this fundamentally different UX to computing in the form of natural language, one thing I was actually hoping to learn from this workshop was ideas on how to come up with the right abstraction for this. It's something I'm struggling with quite a bit. But I do think it presents a lot of opportunities for domain adaptation in the sense that I can now query Zach to write down everything he knows about what it means to build a robust clinical note-taking engine. And if he does, then maybe I have a really good prior. So that's sort of what I meant by human-based domain knowledge. That's not on the web.
However, not saying that the XY paradigm is wrong, but it probably still applies to a lot of things. But to understand these big language models, we need to go beyond that. That's why I'm here. Right? Yeah.
Actually, I would also say that to understand, big language models and big foundation models built on web scale data, I am also not 100% sure if the notion of distribution is super relevant, right? Because in these, in this web scale data, a lot of things, like most of the data is in the tails, right? So we may also, I mean, distribution, it's an abstraction. We all understand, right? Like distribution, the concept of data distribution itself is an abstraction. So maybe we need to rethink.
So the next question then is, where do you go with theory? Because it sounds like, the theoretical construct is that you have differences between distributions, some discrepancy between distributions, something about how the labels have shifted, how the Y's have shifted, and something about how P of Y given X or P of X has shifted. So now we're saying we're getting rid of X and Y and the distributions. So where does theory go now?
I think one of the big challenges, I mean,
jobs. ChatGPT hasn't taken us.
I want to talk to refer to work of Ben that I think one of your 2017 or 16 paper on rethinking generalization, right? That somehow when we talk about theory, we are still confined to the worst case theories and they are not relevant to the world. And we haven't developed yet theories that kind of distinguish what is a realistic scenario and what is an artificial gadget that affects the worst case, but not the behavior in practice. So I think that paper is where I send all my students to start.
Maybe a bit of a controversial take on this is that as someone who's somewhat trained in StatsML, I think I don't really believe in performance guarantees for ML algorithms anymore in the form of theoretical bounds, but rather empirical benchmarking. But then I still believe a lot in how theoretical insights can guide new algorithms. And if you think about how applied econometricians work, they work on the same data for 5 years and they think about the right identification structure, clean the data, run 50 different robustness checks to make sure that their findings are valid. And of course, their problem is never linear, but I think a lot of their papers are actually much more empirically rigorous than an average nerd paper. And that type of a timescale at which empirical research happens, I hope can be somewhat modeled in ML and maybe translated back into our principled thinking. And that feedback loop I'd love to make happen.
I mean, considering that none of econometrics replicates, I'm not sure that's where we want to look for inspiration.
To maybe kind of follow up on Hong's point, I mean, to maybe kind of, sharply.
There's no anonymous here. It's somebody to respond.
Yeah, no one's defending it.
You can tweet it.
I don't think we go to the quantitative social sciences for inspiration. I don't think that's where we need to.
If you can measure something empirically, then you probably don't need theory for it. Is my strong take. Yeah.
I just want to mention that oh, thank you. So it seems like you mentioned that there are some realistic settings, and when we were doing theory, we were talking about distribution free, worst case, everything is like the worst possible thing. And then obviously, when you want to do something in worst case, it's not going to be applicable in real life. Do you think the problem is like sort of lack of the statistical understanding of the distributions that is happening in the real life, or is that correct?
No,
okay.
Give you back your mic.
I don't think that there's any hope that we'll be able to formalize what is realistic scenarios compared to unrealistic scenarios. But we could hopefully, we would be able to reduce the scope from the worst case to something that still encapsulates real world, but is much more reflective of things that can happen in the real world. And I think that's a very important direction to follow. And I mean, when I started thinking about it, it was around satisfiability. We know that survivability is NP hard. We know that SAT solvers are now being employed all over. You have a hard problem, you shift it to a SAT solver. It used to be the case, you have a problem, you want to show it's hard, you reduce SAT to it. Now it goes the other direction. We still don't understand why SAT solvers work. And so it's the same kind of challenge. And I think that there is a hope that we will find some envelope that is not the worst case, but still encompasses most of the realistic scenarios.
Maybe just to respond to what Percy said earlier, I think it'd be good to maybe define what theory means, especially in this audience. It sounds like you mean theory as performance guarantees. Is that, because for example,
I was just like kind of echoing.
I mean, I think just to elaborate on things, like for example, privacy, I think is useful because you can't I guess exactly. I think the definition is you want something by private like construction. You can't just like measure whether this thing is private or not. We've been doing some like watermarking stuff, which is by construction. I think theory is powerful when you kind of can control randomness. I think the theory which requires you to make all sorts of weird assumptions about your data usually ends up in a sort of a hopeless chase of like, what is the real distribution?
Good. On that, I think there's a von Neumann quote I'm fond of, which basically says that for theory to actually have some impact in practice, you really need the theoretician to have great taste. And I think the OG mechanism design people, for example, had that. And their theorems were about people have uniform preferences. And I don't think any of them believed this, but say someone like Paul Milgrom being a clear thinker, I think he wrote down a bunch of mechanisms that are great, articulated some of it in the language of theory, and actually went out and implemented it. So in that sense, I think I have a slightly broader view.
So maybe there's two categories. One is if you want theory to give you actual S numbers that you can use in practice, then it needs to be like by construction. You need to control the randomness, not hope that things are IED. And then there's theory which you do whatever the hell you want, and it doesn't really matter because none of the assumptions are true, but you use good taste and you come up with these brilliant ideas, which then go inspire people.
I mean, I think this is it's sort of a bit of a like red herring, right? I mean, you said before, like you don't believe in performance bounds and all this, but the people who are proving the performance bounds themselves don't believe in these bounds and being useful in practice, right? So it's
I'm one of them.
It's a point being made, but it's sort of like, I mean, I think we all universally agree in this fiction, right? We put the first paper is, xi is drawn IID from px, and at that point already, every mathematical statement I make isn't going to hold in practice. But I guess what the question I have is actually for you, which is, you said before that you think that people with, sort of theory insights, could say something that's useful for what's going on in practice. And my question is, which theoretical is, like, what are some examples, particularly in the context of domain adaptation, covariance shift, all these things, which sort of theoretical insights?
Not in the context of distribution shifts.
Yeah.
I was more thinking about.
So then how do we get there?
Good. I think the timescale is actually a problem. I don't think I'm certainly able to produce any meaningful principled insights in the span of 4 months and publish the next ICMA paper in Adaptation.
So you think it's a cultural problem?
I mean, it might be an intellect problem for me, but yeah, that could be.
See, I don't think we only can judge it in hindsight. I mean, I don't think that we could tell in advance that Hinton is smarter than Chomsky, but somehow
I'll push back a little bit on that, because your talk was, sort of the point of your talk was that, 20 years ago, we had this sort of, feedback loop, right? The theorists were producing their, performance guarantees. And then, like Percy was saying, these, assumptions were restrictive for whatever reason. Then practitioners, empiricists were seeing that, oh, there's some deficiencies in whatever guarantees. And, maybe there was some illusion. I mean, I think Misha had said maybe there was an illusion of some closeness, but there was at least some idea that maybe we're trying to get things to track. Whereas I think a lot of us who are working on these distribution shift things, realize that, in theory, a lot of things are, wonderfully true or wonderfully hard, but in practice, this is just, the gap is, widening day by day. So the question is, we are, as theorists, we try to say something, and then we're finding out, like you said, whatever happens in the real world. But are we really are we, moving towards that ideal that you're sort of hinting at, or not?
So I don't know, maybe I could jump in and say something. So there are two types of theory, right? So one is obviously, the performance bounds and, 1 over square root n or n to the, beta or whatever it is. And then the other is the theory where you formalize something, right? So this is the right way to, I guess the most, one of the best examples of that sort of thing is the paper that defined differential privacy, right? This is the right way to think about privacy, or, the paper that, came up with the frameworks for, back learning or something like that, right? So I feel like in this area, domain adaptation or distribution shift, whatever you call it, that is the part that needs a lot of work, right? We are not there even there yet, right? In a lot of sense, right? So that is one point about the usefulness of theory. So to go to your second point, it is definitely true, right? We don't expect things to depend on the VC dimension. We don't expect things to be, whatever square root 10, but I feel like what a lot of the generalization guarantees or what a lot of learning theory tells us is what are the things that are important, right? What makes a learning problem hard? Well, from VC theory, you can take back the message that if your classifier class is very complicated, then this problem is generalization is going to be hard, right? And, this is a very, very basic example, but there are like many examples of this. So it is true that, we shouldn't take theory at face value. We should take theory with a grain of salt, but these are some insights that you can get from it. I don't know. I mean, would Shai would probably like that.
I took his microphone, so.
I had a quick question on the pragmatic side. I love the last presentation where you kind of mentioned that practically it's actually very difficult to differentiate between interpolation and extrapolation. Like you actually don't know which scenario you're in. And to Zach's point earlier with ImageNet and with a lot of these large language models, when you're, they're trained on internet data and they're applied on internet data, and apparently the internet is infinite and you can just scale internet data. And I think sometimes people frame that as like, to do better out of distribution, quote unquote, just scale the data set. But in some ways, it's just sort of like scaling the data coverage of the types of questions that you're going to ask anyways. And so it's more like in distribution estimation and just scaling within distribution rather than out of distribution. And I think one of the things that I've discovered, especially in like healthcare settings, is that there's a lot of scenarios where it is literally impossible to scale in distribution. So a hospital is trying to, build some kind of internal tool, and they max out in terms of the amount of data that they have available for their patients. And the only option they have is to take data from another hospital. And there have been scenarios like me and Irene Chen worked on a project where we found that, just one, there's like friction to scaling. So, it's a lot of work to get data from another hospital, et cetera. But if you pick the wrong hospital, it actually lowers the performance on the in-distribution data set. And so, yeah, how much of this sort of scaling is all you need attitude, really just like scaling in distribution is great, which is something we already knew, versus actually enabling generalization to out of distribution scenarios. Yeah, and I'm curious, especially for like Percy and sort of pro foundation model folks as well, and how they think about that.
I would say that a lot of scaling is actually all about OOD, right? Because if you take an internet data, most of it has nothing to do with what you're trying to do. And yet you can't, if you try to say, oh, I'm going to select my data that's for question answering, then you do worse. So I feel like the whole story of foundation models is about going beyond the sort of distributional task that you're interested in.
I will add that scaling here also means expanding the set of axes, the things that you can measure. And it's not going to be cheap, right? Coming up with a better data measurement system and all kinds of different resource constraints. But if you have a way to talk about the benefits of adding one more measurement to your database, then I think that starts the conversation. Whereas right now, I don't even know how to even start thinking about this.
Any other comments from the audience or questions, comments? Oh, let's see, go ahead.
I can just, well, I think this may have been asked already by like Samori and others, but it sounds like, yeah. Essentially, so it sounds like we need new definitions rather than more theorems. And it's clear that there isn't going to be one master formulation of demand adaptation or transfer learning. So what do the panelists think are more small carved out pieces of this area where we can aim for new definitions?
Very good question.
I mean, I can say some words. I mean, I think the premise of domain adaptation is, it's problematic, right? Because it's saying, before we had theory for P equals P training equals P test. And now we're saying P train not equal P test. Good luck. And so it's sort of it's sort of the lack of structure as opposed to structure, which is actually where you need to make progress. I think now the question is like, what kind of structure? So we've talked, you can imagine,
going back to kind of importance sampling things where you have
look at the density ratio, which we know is limited. You can look at lower dimensional representations and things. But kind of moving ahead, I kind of alluded to thinking about these, sequence prediction problems. I think we need maybe a definition of how to think about moving away from, XY pairs. Maybe a more tractable thing is where you're still in distribution, but you're just sort of missing data, because a lot of, I think, maybe internet data is like the task is, the answer is sort of written there, but it's just written in a sort of a different form. Like, the question is answered in Wikipedia, but it's declarative as opposed to interactive words written in a different language. So I think one mystery is how language models are able to sort of, look at instances which are, superficially like very, non-overlapping support, but sort of deep down are really the same kind of, instance. I mean, there's other questions around, maybe for language models specifically, like, chain of thought and how that maybe, produces, how that maybe type of supervision helps you maybe alleviate some of the adaptation problems, because you're, looking at the right process as opposed to just the outcome. I don't know, those are some things on the top of my head.
I would say that even in the classical ML regime, I have no way of articulating what my assumptions are on the data and having arguments with you on whether my assumptions are valid. In some sense, if I was to claim that I have some robust algorithm tailored to a particular set of applications, I think it's on me to articulate these DGP assumptions, and then I need to go through this process of debate. And that language and the culture not existing, I think, is something that maybe theory-minded folks can actually try to address.
I mean, I always go back to the need of incorporating prior knowledge, but we don't have good ways of describing prior knowledge, of expressing prior knowledge. And it turns out that, I mean, it seems that foundational models kind of capture some very general prior knowledge in terms of representation, although we don't know how to formalize it. It captures some kind of a very relevant prior knowledge. So I'm optimistic in terms of in the sense that I think that there will be more successes when we use the representation although we cannot explicitly express what prior knowledge they convey.
Okay, that's perfect. So we're going to end on a note of optimism. Okay, so thanks to the panelists. Thanks to all of you for sticking it out on a late Friday afternoon. Yeah. All right, everybody.